Thank you for inviting me to present. It's been very exciting to get to know all of you and learn all the applications and methods people are using bunching for. It's been super interesting, so thank you. Today I'm presenting this paper with Carol and Gregorio on how we can, looking more deeper, I think, on how we can use non-parametric censoring strategies to correct for endogeneity correct to endogeneity when the treatment has a bunching point. And here we're thinking about bunching on the corner in particular. Okay, so this slide you have seen a few times by now. I'm the last presentation, so why it's here again is just my motivation for working on this project, and I think but also motivation to learn these methods and think deeply about these methods is just the large set of possibilities once you have access to these methods, all these interesting causal effects that you might want to identify using them. So I think it's kind of looking back to what we've seen and learned these 2 days is just remember that this is useful and interesting because you can apply a lot. So going straight to what we do in this paper, we're going to be thinking about identification using bunching on the treatment. And kind of we're going to make, I would say we'll make a point kind of very directly. We're going to show how to recast bunching on the treatment variable as a non-parametric censoring model. And why do we like that? We like that because there's a very large literature on censoring since Powell 1984, more recent contributions, and we can basically use these off-the-shelf methods to identify our causal effect. Kind of the cost to have access to this large library will be a linearity assumption that that's the difference to Carol's what Carol presented earlier today. But kind of if you buy the linearity or you think it's a good approximation to your setting, then you have access to this very large literature. Okay, so this is kind of the paper in one slide. So what I'm doing today, I'm going to give you basically a minimal setup to understand the problem, understand identification. Then I'll also go through a minimal argument, graphical argument for identification, or how I think about identification in this setting. And then I'm going to think about how we can recast bunching in this non-parametric censoring model. And I'm going to zoom in one particular non-parametric censoring strategy that we like. We think it's very flexible. It seems to work well in applications, and I think it's kind of quite interesting. So I think, and I would love feedback on what do you think, if you think it's useful. Okay, so for the setup, we try to be as minimal as I can be. We're going to have a treatment, a non-negative treatment X that will have bunching at 0. I will, as the other papers, introduce this selection variable X star satisfying this equation. I like to write the equation like this because for me it looks very much like a selection equation in the sense that if you have X star strictly positive, then you're selected into treatment. And that determines your quantity of treatment. But that basically is saying that when X star or the treatment is strictly positive, it equals X, when the treatment is strictly positive, then it equals X star. And on the other hand, when the treatment is 0, that's the key kind of intuition. We only know that X star is non-negative, but we know presumably there is variation on X star that is this variation on underlying on this underlying selection variable. Okay, so the idea of the people at bunching point differ on their own observables, even though they don't differ on the treatment that they get. Okay, and I'm just going to assume that X star is strictly negative with strictly positive probability. Okay. Okay, so for potential and observed outcomes, we're going to have a very general potential outcome function. When evaluated at little x, that's just the potential outcome for treatment level little x. Note that the variable that determines the observed outcome is the actual treatment x, not x star. And therefore, for all bunched units, the outcome we observe is the untreated outcome. So even though there's a lot of variation underlying on this underlying unobservable characteristic X star, all observed outcomes there are the untreated potential outcome. Okay, and then this is just like this will be the implied notation for observation-specific causal effects. Okay? So this is a very natural, I think, and very kind of minimal setup. So given that, let me talk to you through our target parameter. So to define it, I would essentially assume that the support of the treatment variable is continuous near zero. This gives me like the technical framework to define the target parameter. The idea is that you have bunching at zero, but then the distribution around zero is like continuous. It doesn't need to be smooth. It just have to have some mass there. Okay. Given that, this is what will be our target parameter. It's the same as Carol presented before. So that's the, so if you look inside the expectation here, this is just the ATT at X per quantity of treatment. It's an ATT because you're conditional on X equals X. And basically we're taking the limit when X goes to zero. So this is like, we're taking as given that this is the parameter of interest. Some more easier we believe and we argue that this is like per se a economic quantity of interest, but as Carol argued, if you're willing to make stronger assumptions, you get different interpretations as derivatives of the underlying potential outcome function. I'm leaving that aside for now. Okay, so just a kind of, I think, to have in mind that the existence here, even though it's like a technical condition, and it is a technical condition, is the right differentiability of the ATT function, it also kind of encodes some substantive or economic restriction, right? As Greg and Carol pointed out, the treatment, the ATT function cannot be, it has to be sufficiently smooth in the sense of being differentiable at zero. So this has some economic meaning. If you think your treatment effect is very discontinuous at zero, then this what I'm showing for you today won't carry over okay? Okay, so given the target parameter, then the other assumption would be a linearity assumption. Here, I'm going to make it only kind of exactly where I need, in the sense that I'm only assuming linearity of the expectation, the conditional expectation. Sorry. I'm only going to assume a linearity of the conditional expectation of the untreated outcome, potential outcome on X star when X star is negative, okay? So that kind of contrasts with global linearity. This basically means that at the bunching point, this expected difference on the outcome, which is the untreated potential outcome, are proportional to variations on the selection variable X star. So this kind of plays, in some senses, also restricting on how we think about the selection variable on the negative side. It can be a lot of things, but it should be something that is proportional to variations on the when you compute the expectation, you get a linear expectation, conditional expectation. We're also assuming that this function here, basically the map from like the conditional expectation of the untreated potential outcome on the selection variable is differentiable at zero. Again, as the other differentiability condition that I showed you, this also has some economic or / substantive interpretation. You need that on average, the untreated potential outcome around the bunching point is comparable between observations. So this is what is going to give us comparability between those exactly or with X star equals to zero, so marginally they are just like indifferent at the bunching point, to those that have a strictly positive treatment. So that's also like a substantive assumption. Just here a comment. This can be easily relaxed to a random coefficient models. So say if you have covariates in your data set, you want to make these coefficients dependent on those covariates. That's very easy to do the theory, but also to implement, in the sense that in kind of the easiest case where those in the easy case where those covariates are discrete, you just subset your data and do whatever I'm telling you to that subsample, and everything will carry over. with the additional advantage that you have conditional assumptions now. So they're all conditional equivariants. Okay. So this is the setup. So treatment with bunching, selection variable, potential outcomes virtually unrestricted, except for this quantity, and the treatment effect function, the ATT function, differentiable at 0. Okay?
Sorry, just clarification. So this is for all xi smaller than 0.
Yes, yes, yes. So the idea here is that the conditional expectation is linear, but it has to hold with probability 1 when x star is negative. Okay? So this doesn't have to be true when the treatment is strictly positive, and also doesn't need to be the case that every y0 is a linear function of x star. It's just the expected y0. Okay. Okay, so identification, let me give you kind of how I view identification here, and graphically, I think that helps a lot, or helped me when I started thinking about this. So here, this is what we observe. So in the x-axis, we have the treatment, and actually we don't observe the selection variable, the negative side, right? But there's nothing here yet. We observe the treatment and the selection variable on the positive side. And we also observe the conditional expectation of the outcome on x, on the treatment. As most of the graphs the applied presentation showed, we have a discontinuity at 0 here. Okay. So, but the thing is that this conditional expectation of the outcome on the treatment is kind of the combination of two underlying processes. First, the ATT function on x, on the treatment, but also the conditional expectation of the untreated outcome on x star. So in the positive side, when you sum these two dashed lines, you get the black line because x star and x are the same. But here at the bunching point, JTT is 0 because I observe the untreated potential outcome, right? So this quantity here, this difference here will be 0. But so what am I observing? I'm observing just the integral on this negative side. So I observe on the strictly positive side the combination of these two underlying functions, and on the negative side, the integral on the negative side of the untreated potential outcome. Sorry, on the bunching point, the integral of the untreated potential outcome on the x star when it's negative. So given that, yes, given that this is what I observe and what I like the underlying processes, if I was trying to estimate the target parameter that the derivative of the ATT function at 0 in a naive way, what could I do? I could try to estimate the derivative of the expectation of the observed outcome on x near 0 at 0. That would be naive, and why would that be naive? We know that this combines the slopes of these two underlying processes, the beta 0 plus that I want, this derivative of the ATT function, but also a selection bias. So that's kind of, this is just like a continuous version of the equation you see on, I don't know, chapter 2 of Mostly Harmless Econometrics or something. So whatever you observe encodes two underlying processes, select a treatment effect, but also selection. What is nice, and notice that here it's linear, so this is the slope, it's a global slope, or global in the negative side slope. What is nice about bunching is that this discontinuity under the linearity assumption maps to the selection bias coefficient that I want to identify to correct this thing that I observe to get what I want, times this expectation of x star on the negative side that I don't know. So just formalizing this, my target parameter equals to this derivative that I can compute in the data, minus a correction term that is based on the discontinuity of the outcome at the bunching point, that I can also compute at the data, divided or rescaled by this expectation of x star on the negative side. So I went from, I want to identify the target parameter beta 0 plus to it's sufficient now to identify this quantity here. What is the problem that we know by now is that we don't observe x star on the negative side, so this is not identified without further assumptions. But let's think a little bit more about that. So notice first this equation here at the top. I'm just rewriting, it's not nothing fancy, I'm just rewriting whatever I already showed you. So x star equals x when x is positive, true, and x star equals itself when it's negative, right? That's just like a tautology. But let's take expectations on both sides. We just linear, expectations are linear, we get this nice equation. If we like iterate expectations here, we get exactly what we need to identify times the probability of x being negative. The probability of x being negative, it's nice, it's just the probability of bunching. So now we kind of can map what we want to identify and we don't know how to identify to this other quantity, the expectation of x star not in the negative region over the entirety of the support. So, okay, but it feels a little circular, no? Like, oh, okay, I'm saying I don't know how to identify this, and then I write it as something that I also don't know how to identify. So what are we getting? So we get the following. So assume you observe a vector of covariates, and I think all data sets that I know have covariates in them, so that feels like a very cheap assumption. And define m of z, this function, as the conditional expectation of x star on z. So this is just a definition. So now, identifying whatever we wanted is equals to identifying the expectation of m of z. So notice that I don't have the red on the expectation anymore, only at the function m. Why? Because I know the distribution of z. I observe z, so that's identifiable. So now I actually don't need to identify the expectation, I just need to identify m. Okay, so I went from identifying this quantity, the expectation of x star on the negative side, to identifying this function m. That is by definition a conditional expectation of the selection variable on z. These covariates that whatever you want them to be, okay? So just rewriting my problem, now it's sufficient to identify my target parameter to identify this functional, this function, a conditional expectation. But recall that by definition, these two equations hold. So first, the selection variable equals m of z plus an observable term, but that an observable term is by definition mean dependent of the covariates. That's just by a nature of how I defined m. And this is just rewriting that the equation defining m star, right? This is just a recasting of my first equation in the setup. So but these two equations together define a standard non-parametric censoring model, but more than that, define a standard non-parametric censoring model where the mean dependence condition holds for free, in the sense that it holds by definition, okay? And then this is kind of the first, I think, first message here that I would like you to get is that, oh, sorry, yeah. So MZ is one of the main objects of interest in the censoring literature. So kind of an idea, choose whatever method you want from the censoring literature and plug it in this formula. And that's kind of it.
Can you maybe show a little bit where the linearity assumption kind of like is showing up here?
Yeah. So linearity comes maybe here. Here's the best way to show it to you, I think. So what is this difference here? Is basic. So when I compute this will be the expectation of y0 on the negative side. This will have an intercept component and a slope component. I difference out the intercept component taking the limit here. So this term here gives me delta. So this big delta gives me small delta times the expectation. and then divide by the expectation to get the little delta. Does that make sense? It's basically a map. Linearity is used to map whatever selection term I had to the expectation here.
Basically, that just makes the problem into a single.
Yeah. If I had a nonlinear function here, say that I had a polynomial function on the negative side, not linear, then I would need the expectation and the variance. And if I had a third order function, I would need the expectation, the variance, and the third moment, and a fourth order, and so on. But then there's a trade-off between identifying expectations and higher order moments, because then I need more of the distribution.
It is my understanding that David has an empirical paper that he's trying to work on, where he's exactly trying to do that. He's allowing for the second moment and third moment, because if you think about it, if you look at the empirical distribution of zero, you can get all those moments in principle, right?
Yeah.
But we can talk about this. At least he did talk to me about this paper one day.
But the caveat in some sense is that if I need more moments, then I will need to identify more of the distribution of X star, and that generally requires more structure. Here, I'm going on the other way, imposing linearity that's stronger, but then relaxing to the most we can the distribution of X star. And I'll show to you what I mean by the most we can. Okay, so I was here. Oh, so yes, here. So this is the idea. So choose your favorite identification method and plug it in. There are a lot of identification methods you could plug in. So there's a long literature initiated by Powell modeling M as a linear function of Z. A lot of possible estimation strategies there, and semi-parametric, like partially linear modeling for M. What I'm going to show to you, and I'm going to zoom in, this Shen, Dao, and Kun paper from 2005, that is, we'll let M be non-parametric, and we will only make non-parametric assumptions on the conditional distribution of X star on Z. In particular, we'll have a non-parametric location scale assumption that I'll detail better. So as an aside, before going to the non-parametric method, I just would like to talk a little bit more about Z, the covariates that I introduced. So I introduced covariates here to recast from identifying the expectation of X star to identifying this function, this conditional expectation function. But I didn't say much about Z. I didn't say much about Z because I don't need to. First, Z is not a control in the outcome model. I don't need anything like selection of observables, like, oh, the error in the potential outcomes are independent of something conditional on Z. I don't need that. We can also let, kind of related, we can also let Z and eta to affect or be correlated to potential outcomes without restrictions. And more than that, the relationship between Z and X star is not of interest here, in the sense that M is just a conditional expectation. I don't need to assign any structural, in the sense like economic or causal interpretation to it. Relatedly, eta, this kind of, is just a projection error. It's by definition mean independent of Z. So this gives the researcher, and I guess we like this quite a bit, it gives the researcher a lot of freedom to choose Z. How should you choose Z? You should think of, it's a match between whatever censoring method you would like to apply to identify the expectation of X star that motivates your choice of Z. And if you have Z's that are suitable for one method, then maybe pair those Z's with that method and so on.
So yes, I understand that there's a lot of freedom in choosing Z, but at the end of the day, you're going to be using the relationship between Z and X star and the part that you observe to extrapolate, even if it's super flexible non-parametrically, to the side that you don't observe.
Yep.
So if you can find a story or something to justify the Z's predicting the selection variable, you're definitely in much better shape than if you just pick some random stuff that you generate on a computer or are related at all to the selection, right?
Yeah, if you generate Z random, like, the limit you could generate Z as like a uniform on your computer, that won't work, because then the assumptions won't. Like,
or any variable that you may have, right? It's
exactly.
something that's caused after or something.
Exactly. So you want, what I mean in this slide is that, as you mentioned, what we care about is how Z predicts X star and how does that relate to our non-parametric, or like our method to identify the conditional expectation. We don't have to care about the outcome here. We can even use separate data sets if you want. One with X and Z and one with the outcome and X. That's fine. You don't need to have a connection between the outcome and Z in no way. But yes, you would like there, M is a predictive relationship of Z on X star. So that's kind of where you should think about how you should think about your Z's. And then also the other assumptions, the parametric, the censoring methods we require. Okay, so now, how much time do I have? Okay. Okay. So I'm going to walk you through this method of Shen et al. 2005, because I guess we liked it and it feels very flexible. I think it's very nice. So first, a lot of math and then pictures. I think the pictures will probably be more informative than the math, but the math is here just as to guarantee that everything is kind of well defined. So this first assumption will be a restriction on your data, basically, that you can easily look at your data and you can verify it. So let Q of Z alpha be the alpha quantile of the distribution of the treatment condition on the covariance. We're going to assume two things. First, there will exist some value of your covariates such that for a known and fixed quantile alpha star, that quantile is strictly positive. What does that mean is that you can find a value for your control such that you have less than alpha star bunching. Second, we're going to assume that for all value of your controls, you can find two quantiles that may depend on the controls you're looking at that are strictly positive and finite. So this, you can plot the conditional distribution of X, or of your treatment on your covariates, and check these conditions. The other assumption, it's the location scale assumption. This is essentially non-testable. We're going to assume that the conditional distribution of that projection error, that like residual on X star after you partial out the covariates, belongs to a non-parametric location scale family that's centered on alpha star. So I think it would be better to explain to you what that exactly means using the graphs, but what is important here is this non-parametric family. I don't need to know or identify or estimate H for the method to work. Of course, it nests any parametric location scale family, say normal, whatever you can think of, but it's more general than that. So how does that look in the graph? So here I'm thinking of binary Z. So first, note that I'm going to think of alpha star as the medium for the remainder of the talk. So it's 50%, right? So first, why is this location scale? Note that the picture on the right is just like a left shift. I took the mean and put it to the left of the distribution on the right. And the scale is shrunk. So here I had like a large, you can think of as a variance, and I just shrunk the variance. Okay. Note, however, that there's no symmetry assumption here. this side is very different from this side. But the thing is that this distribution is, I draw in a way that is centered at the median. Okay? I should have mentioned earlier, but the x-axis is x star. And whatever this dashed part is the distribution of x star. In black is the distribution of the treatment with the bunching point here. So let's zoom in on z equals 0. Because it's centered around the median, then the mean is the median. Okay, so that's the easy case, when the median is strictly positive. However, when the mean is negative, I cannot look at the median will be 0. So what can I do? I can look at pick the two quantiles that are strictly positive in both distributions, and use the location scale that is non-parametric to connect quantiles, some quantile alpha, say this first one here, to the quantile to the same quantile here. This will depend only on the conditional mean, conditional z equals 1, and the ratio of scales. However, because I have two quantiles and this is a system with two unknowns, the ratio and the mean, since I have identified M0, I can use those two quantiles to recover, like solving a linear system, to recover M1. And then after I have M0 and M1, I just take the expectation across the distribution of Z. That I know how to do because I observe Z, so I know the probabilities of Z equal 1 and Z equal 0. So this is just the formal result, just to say you don't have to go yourself and solve the system. We already solved and plug it in. It's going to be like a combination of quantiles, and the coefficients are linear, and like to find them, you just have to compute a bunch of other quantiles. But okay, so hopefully you got how I'm identifying this in this case. But this is a flexible method in a number of ways. So first, notice over-identified in many applications. Why? I used z equals 0, and that I found M0 to find M1. But suppose that I also had z equals 2, where the median is also strictly positive. Then I could also use M2 that equals the median I can identify to recover M1 in a different way. And I can recover M1 in two different ways. Therefore, I'm over-identified. I also use two quantiles because I want to like a just identified linear system, but I could use, say, 10 quantiles. And then that system of equations that I showed you that it's still on two unknowns, I have two unknowns, 10 equations. I can recover all of that in an over-identified way. So in practice, that leads to like efficiency gains when you're estimating. So okay, I have to estimate quantiles, take ratios, invert, and solve a linear system. Will that be noisy? Yeah, it could be, but because you may have a lot of over-identification, that helps you reducing those standard errors. Second, the center of the median restriction, I use that only for one thing, to recover M0. So any other type of restriction that recovers M to a single point is sufficient, and then you just use the location scale restriction to kind of drop all the other dominoes. In particular, one that I think might be very intuitive is say that in an application you find a control where you don't have bunching condition on that control. You have zero bunching. Say people that, I don't know, that work, a type of people that work a lot when they're 65. In that case, the mean of the treatment is the mean of the selection variable by definition. The selection variable equals the treatment at any point, and then you have recovered M for that control variable, and you can use it to drop the other dominoes and identify M at every point in the support. And finally, it's very, as I mentioned before, it's very easy to adapt the assumptions to hold only conditional order controls. In practice, running subsamples. Then this has to be true only conditional covariates. Say that Z is race, you think these assumptions only hold condition on gender, subset for each gender that you have in your sample, and then run it separately. Okay, that's identification. For estimation, I won't have anything super, I guess, 2 minutes, okay. Super insightful to say. You just estimate M and plug it in. It's not much of a secret, I guess. In the paper, we consider estimators M hat that result in root N consistent estimation of the expectation. That's just like follows from standard conditions on two-step estimation. And then if you do non-parametric estimation of this term and this term, then it's easy. Inference is easy because this will converge way slower than everything else. You just use the standard errors from this part. And we also discuss, for those who like linear models, if you think the expectation of the outcome on X on the positive, strictly positive side is linear, this can be done using OLS. So you just generate this coefficient. It's like a constant for every Z. You generate this associated regressor and you run OLS. And then the coefficient on X on the treatment will be the estimate of your target parameter, if you believe in this linearity assumption. And then we compute standard errors and so on. Okay, so summary, I think I'm on time. So we consider, we're thinking about these ways to correct for selection bias when the treatment has bunching on the corner of the distribution. The correction relies on linearity of the expectation of the untreated potential outcome on the selection variable. That's, to Stefan's point, is to map selection bias to the expectation of the selection variable on the negative side. And then the first point that I think is kind of the novel point is that you can go from identifying that to just identifying a conditional expectation of X star on Z, and then integrating over the distribution of Z. And then this gives you immediate access to a large library of methods in the censoring literature. And in particular, we focus on this more flexible non-parametric in which all restrictions either on the distribution of X star or on the conditional expectation of X star on Z are non-parametric. And that's kind of what I had for today.
Has any questions?
Thanks a lot. This was terrific. I have, I guess, two questions. First, when you're choosing the Z, it feels that a Z that's highly predictive of X star would be helpful with the variance of your estimator, for much the same reason as a Z that's almost independent of or completely independent of anything, like random number generator wouldn't work. So it looks like, I mean, it just, what do you think of this?
Yeah, I think I'm trying to remember the formula for the variance of this thing, but I won't be able to do it right now. But I think you're correct. Like, because you want to estimate M in the best way possible, right? So that I'm not sure if it's about the predictive. Let me try to do an analogy with OLS. Say that you have, if model was linear, it was beta of Z plus an error term. It's true, the beta can be 0 or could be close to 0. In that sense, we wouldn't predict very well. But the variation in the error should be small for you to get a good prediction, a good estimator for beta, right? So if you know, as your residual has small variation, then you get a good prediction for beta. Here is that notion of predictive power, yes. So the variance of eta, the prediction error, should be small, and that will that will map to the variance of your estimator m hat. By that definition of the quality of prediction, then yes, you're correct.
So, Otavio, there's something that's, I don't know if it's in the theory, but certainly in the computation, there seems to be like an edge condition that's kind of hanging because you're dividing, right? By that condition expectation of that, of m minus x, the expectation of it. So there must be, there's cases when this gets close to zero that theoretically you might exclude, but then when you're doing the computation, it seems to be that it's going to generate some problems, or the user, or that's something that's applying your method might get some problems when you're dividing by zero. So I don't know if you've thought about that, check that when you're estimating, because even if you have some conditions in your theory that exclude that dividing by zero case, when you're estimating just by chance, there might be points that are close to zero and might just make things blow up, and you need to either control, trim, or do something about it. And so I don't know, it's kind of like, I was just staring at it. It seems to be that there seems to be an edge condition there.
Yeah, so in theory, we get rid of that by assuming that the probability of x star is strictly negative, is strictly positive. That's kind of the easy way to get out of that. In practice, so I think I have two things to say. First, on the applications we have, it doesn't feel like to be the case. The expectations seem to be on like -10 or something, -12. Note that mz for a particular value of z can be very close to zero. That wouldn't be a problem. Yeah, and it's kind of, when you integrate over z, that should, so I think that buys some type of robustness, but it's true. If you have something that is very close to zero, then first your estimate will blow up, but also your standard errors are going to be very large, because you're dividing. It's kind of a weak IV problem in some sense. Like you're dividing by something that is close to zero, things blow up, your standard errors also blow up.
Fabio, just one detail is that if you have, if your distribution, all right, cannot like just suddenly go up on the negative side, like in some way like that, you have a minimum expectation dimension, let's just say, which is like lower bounded by the uniform. So already by just not having something very weird coming up. So if you have a distribution like he's showing, you would have to have a distribution that suddenly goes up a lot and kind of remains around that point for you to have a low expectation. For the expectation to be zero, yeah. So if those functions are somewhat more, in any way, like not going crazy in that sense, there's already a lower bound on the magnitude. Yeah, you will have to have it going up and staying very close to zero. No. It will have to go up and stay. Like you have to huge mass there. Then
because if on the left side is the maximum density is giving it by this point at zero here, then the bound, as Kara was saying, is like you have to do a uniform that integrates to the bunching point, and that implies your conditional expectation on the negative side has a strong lower bound that is bounded away from zero. And the larger the bunching mass, the larger that the lower bound is in absolute value. Yeah, if your bunching is very small, like 1 or 2%, then it's hard. Yeah.
So one comment is that the moment you transform the whole problem into a censoring problem, now you have this whole library of ways to go after the selection effect. This is a little bit like a crazy assumption that perhaps for the future, but one option would be, of course, to use multiple approaches. Each of them would have non-nested set of assumptions. And then I was just wondering, some form of model averaging would be a useful way to go after the that expectation, and or perhaps to handle issues like the ones we were talking about. Perhaps we could even think about trimming. Uh, that those are they're close enough to zero. And anyway, this will be interesting, perhaps avenues to go for. Even ideas like the placebo idea that David was discussing, to use that as potential ways of projecting that.
Yeah. Thank you.